Okay. Number one, use an appropriate linearization to approximate 1 over root 10. I don't know what 1 over root 10 is. I know what 1 over root 9 is. So my function, what would be an appropriate function? Okay, I'm going to say f of x is 1 over root x. And I'm going to say a equals 9, because I know what f of 9 is. That's 1 over root 9, which is a third. That's like my anchor. I know what a third is. What's the linearization? So root x, 1 over root x. 1 over root x looks something like that. Over here at a equals 9, I have the value 1/3. I want to find the linearization. That's the linear function L, which is the approximation at this point, and I'm going to evaluate L at 10. Okay. All right, very good. So what is L? Well, the derivative of x is x to the minus a half. So I get minus a half x to the minus 3/2. Is that what you got? And I'm going to evaluate this at a equals 9. So at a equals 9, evaluate at a equals 9. Notice I'm not just saying equals negative a half, 3 to the, I guess this would be 9 to the 3/2. Don't just write equals. Don't write equal signs that are false, right? So I'm evaluating this at a equals 9. I'm evaluating this at a equals 9. So that's x to the minus 3/2. That's an x to the 3/2 in the denominator when x is equal to 9. 9 to the 3/2. Square root of 9 is 3. Cubed is 27. So I get negative 1 over 2 times 27, 54. I really hope you guys are checking this because I'm going very quickly and I'm not confident in my arithmetic. That seems about right. Negative 1 over 54 is about the slope that I would expect from the picture, right? So check kind of every bit of your understanding. All right. And so what would be the equation would be y minus a third is equal to negative 1 over 54. I'm thinking of this point, 9 comma a third, as a point on the line with slope negative 154. So this is x minus 9. And so L of x is this is the equation of the line. So I'll move the 1/3 to the other side. So negative 1 over 54 x plus, oh God, 9 over 54. 54 is divisible by 9. It's a sixth. So this is plus a sixth plus another third. A third plus a sixth is a half. Oh, that's nice. Okay, so this line, if I had extended it, would go through a half. That's all that means. Fine, whatever it is. Find L of x for my choices. Done. That's part B. This is part B. Part A is right here. These two things are part A. This is part B. You see how I'm trying to organize so that whoever's grading this looks at it and instantly understands what it is that I'm doing. Okay. C, find dx so that a plus dx is a 10th. Well, dx I would say is 9. So dx, so this is part C, dx is 1 because then f of a, which is 9, plus dx is 1, is f of 10, and that's exactly 1 over root 10. Okay, so for part C, find dx, so dx is 1. Right, I'm moving one step to the right off of my anchor. This distance is dx. Okay, and find a standard linear approximation for 1 over root 10 using my choices. So in other words, I'm going to approximate, so part D, I'm going to approximate f of 10 as being roughly L of 10. Instead of the true value, here's my picture, instead of the true value on the curve, I have the value of the linear approximation, and L of 10 is, if I put in 10 here, negative 10 over 54. Don't bother simplifying that. There's a 2 on top and bottom. Who cares? Plus a half. That's it. That's it. That's the linear approximation to 1 over root 10. Any questions on number 1? How many would have gotten this one? Nice. Next, number 2. One side of a house has the shape of a square surmounted by an equilateral triangle. Okay, wait a second. A square surmounted, i.e. the equilateral triangle sits on top of the square. Okay, that's what I would think. Okay. One side of the house has this shape. All right, I can imagine that, right? Whatever. Not a colonial. Is it a colonial? What is this? So one side of this is all I care about, right? This is the rest of the house, but this is all I care about. This is the side of the house. The base is measured as 20 feet. The base is measured as 20 feet with a maximum error in measurement of 1 inch, give or take 1 inch. Use differentials to approximate the relative error in the calculation of the area of the side of the house if the measurement of 20 feet for the base is used. Okay, so let's put in some variables. Let's say this is S. Okay, so the square has area S squared. What about this equilateral triangle? Ugh, I got an S here. I got an S over 2 here. What's the height? Yeah, 1/2 root 3 over 2, right? You guys know your 30, 60, 90 triangles. This is an equilateral triangle, so this is a 60-degree angle. Okay, so the area, so the total area is the S squared on bottom plus root 3 over 2 S times S over 2. Well, it's 1/2 of S over 2, but there's 2 of them. So what is that? Root 3 over 4 S squared. Okay, so you can combine this if you like. It doesn't really matter. That's 1, which is 4/4. So that's 4 plus root 3 over 4 S squared. So root 3 is the height. Root 3 over 2 S is the height. S over 2 is the base. So the area of this is 1/2 base times height, but there's 2 of them. So no 1/2. So base is S over 2, and the height is root 3 over 2. So if I multiply those two together, I get root 3 over 4 S squared. Yep. Okay, so now we have A as a function of S. A, this total area is A. I'm just writing it in for some ungodly reason. So what do I know about dA? The change in A as S changes is 4 plus root 3 over 4 times 2S times ds, right? This is differentials. It's like implicit differentiation, but with no, with respect to what? With respect to nothing. With respect to time or with respect to measurements or something. Okay, so S is 20 feet. What are we going to do for this area? Is it going to be in inches or feet? I guess more, it looks like feet is, it didn't say in what, it didn't tell us, right? If it wants it in feet squared or inches squared. Let's make it feet squared. So this is 20 feet. ds is 1/12 of a foot. So that's it. The area, so the measurement in area, so the relative error is not the proportional error, is it? What's relative error mean? Relative error just means what's the error in the measurement of, area, right? It's not the percent error. Let's calculate both just in case. So dA is very simple. It's just this constant 4 plus root 3 over 4, I guess times 2, whatever. Don't bother simplifying unless it's not going to say simplify. 20 feet times 1/12, and this is feet squared. Okay, so this is the error in our approximation. So the area, we think the area is 4 plus root 3 over 4 times 20 squared, and this is the error in that calculation. What would be the percent error? Maybe this is what they mean by relative error. dA over A, I would be more precise in my terminology. I would try to be more precise in my terminology. That would be the percent error. Percent error. How big is the error as a fraction of the, how big is the error? Error and area are two very similar sounding words. How big is the error in the measurement of area relative to the area itself, the size of the area itself? That would be the ratio of this thing, 4 plus root 3 over 4 times 2 times 20 times 1/12, divided by the actual area, which is 4 plus root 3 over 4, that same constant, times 20 squared, and that's it. And I've written it out like this because I see a lot of things are going to cancel. And so now I can actually work this out. 2, that's a 1/6, 1 over 20. This is 1 over 1/20th or something. So that's the percent error in this estimation. Okay? Does that make sense? I think this is what they mean by what is the error. The word relative scares me a little bit. So let's go over our vocabulary. Maybe somebody can look. I don't know what if the book calls this relative error. I think they call it percent error. What does it call? Relative error. So, okay. So good. So relative error means percent. It's a good thing we did both. Relative means percent error. Okay. So that's this one. So the percent error. What's the dimension of the percent error? Dimensionless, because dA is feet squared. That's how much you expect that error to be. A is feet squared. So when you take the ratio, it's dimensions. Okay, very good. Any questions? Did we get this right? Is anybody checking anything? Yes, thank you. Okay, consider this function. Find its critical points. Great, I know how to do that. F prime of x is equal to -12. Okay. Let's leave this alone. X to the 1/3. We're using the product rule. Times the derivative of what's inside is 4x plus 14. Plus, I'll leave this alone. And what's the derivative of x to the 1/3? 1/3 x to the -2/3 times 2x squared plus 14x minus 70. Okay, so that's the derivative. Let me pull out an x to the -2/3. So if I have this -12, I'll pull out an x to the -2/3. That's like multiplying the top and bottom by x to the 2/3 and making this the bottom, x to the 2/3. So what am I left with here? Instead of x to the 1/3, I have x. So this is x times 4x plus 14 plus, I guess, the 1/3. Nothing I can do about that 1/3 plus 1/3. I guess I could pull the 1/3 out and make this a 3. Let's do that. That'll be good. Pull the 1/3 out, make that a 3 so that I don't have fractions in here. Fractions are too hard for me. 2x squared plus 14x minus 70. Okay, so far so good. 12 over 3, even I can do that. And I get a 12x squared plus 2x squared, 14x squared. I get 14 times 3x and one more 14x. So that's 14 times 4, 28, 54. Although I do see that I should have left it as 14 times 4. Let me leave it as 14 times 4 because I have a 14 here. 14 times 4x. And then minus 70. So minus 70. Is 70 14 times something? Yes, it's divisible by 7 and by 2. So it's 14 times 5. That sounds right. 14 times 5. Aha. So that 14 can come out. -4 times x to the -2/3 times 14. And I'm left with x plus 4 times x minus 5. I think I can factor that because I need a plus sign and a minus sign. I want the sum of two things to be 4 and their product to be -5. So I add 5 and subtract 1. I think that's right. So I didn't even need, okay, if you didn't see this and you did the quadratic formula, no problem. I hope you saw to factor out the 14 so that you're not stuck doing a lot of arithmetic, hand arithmetic, which would be annoying. Like squaring this number would be pretty annoying. So try to look for things that simplify your life a little bit. But okay, that means we know the critical values. The critical values are where the derivative is 0, and that's x equals 1 and -5. Good. Good. It's where the derivative is 0 or it doesn't exist. And it doesn't exist because there's a denominator blowing up. And x equals 0. Do not forget this critical value. Okay? So that was part A. Find the critical points. Great. The critical points, critical values are x values. Critical points are x comma y values? Or just x values? What are critical points? The x's and the y's. So I have to stick in 1 for x, and I have to stick in 0 for x, and I have to stick in -5 for x. I'm not sure. I think it's just the critical. I think it's just they just want the x values. What do you think? Just the x values? Yeah, it's this is how people abuse language. Okay, so it should by point it should be in a point on the curve, right? These should be the points of criticality or something. All right, find the local maxima and the location where they occur. Find the local minima and location where they occur. Fine. Local maximas and mins are determined by the sign of f. So what's happening? F prime. So let's look at f prime. So this was part A, the critical values. We don't need to plug in x equals -5 and square -5 and take the cube root of -5 and do all that stuff. So here's the graph. I have a 1, I have a -5, I have a 0, and I have a 1. Now, what's happening when the number is huge? When x is huge, this is positive, that's positive, that's positive, that's positive, that's a minus sign, that's positive. So it's positive when x is huge. What happens if x is huge and negative? Huge and negative means this is negative, this is negative. These two things are, well, that's negative, and this is x squared to the 1/3. So this is always positive, right? X to the 2/3 is always positive. So what did I have? A minus sign here, minus, minus. That's 3 minus signs. That's a minus sign. Did I get it wrong? When I go 1 and above, everything is positive except for that minus sign. Thank you very much. Okay, you should always check your work. I always say everybody can make mistakes. I hope I demonstrate that. And also the correction of it. Of course, I don't have Vi to, you won't have Vi to look over your shoulder. You should have yourself look over your shoulder. Okay. When I'm between 0 and 5, again, this whole part is always negative. Let's just remember that. This whole part is always negative. Between 0 and 5, this part is, I'm taking something negative and subtracting 1. This part's negative, and this part is positive. So that's a plus sign. Because that's negative and another and a negative. And how about here between 0 and 1? If I take a number between 0 and 1 and I add 5 to it, that's positive. But if I take a number less than 1 and I subtract 1, I get something negative. So this is negative times a negative. This is also positive. Yeah, does that make sense? So what's going on? -5 is a local, we were decreasing, then we're increasing. Decreasing, then increasing is a local min. So this is local min. Local min. Increasing, continuing to increase. Now the derivative here blows up. So how can we be increasing and then we continue to increase? It probably is something like that, and then something like that, where it's increasing and it continues to increase. Well, that's the derivative. What's happening to the function itself? The function itself has no blow up. There's nothing wrong with taking the cube root of 0. So this is f prime. The function itself probably looks something like this. It's increasing, infinitely increasing, and then it starts out infinitely increasing, continues to increase. Okay, so this is f. I'm just guessing near 0. Near 0. At -5, I have a local min, wherever that is, -5. At 1, I'm increasing, and then I start decreasing. As soon as I cross 1, local max. This is my local max. Okay, so at 1, I turn the corner and I start decreasing. Okay, that's where f prime goes from negative to positive, and -5 is where f prime goes from negative to positive. And here it blows up. Something like this. Actually, it's positive on this side, right? So that's not a good picture of f prime. It's positive, and then it becomes negative. So that's a better picture of f prime. Just the signs of f prime. The sign is negative, then it's positive on both sides of 0, and then it's negative. So f looks something like this. Caitlin. So f prime has a 1 over x to the 2/3 in it. So it's blowing up. And it's blowing up in a positive. It's positive on both sides. So the function's increasing and then it continues to be increasing. Okay, does that make sense? Did we answer the question? What's part B? Find the local maxima and location where they occur. Okay, and find the local minima and location where they occur. So local max at x equals 1. That's B. Local min at x equals -5. Now, by location where they occur, now do they want me to put in -5 for x? Give me the point, Sid. I will try to be very precise in my words and make sure that you know what's location as a point or location as an x value. Okay, that's on me to make sure that my language is unambiguous. So far, so good. Next. Okay, find the absolute value, absolute maximum and minimum values where they occur for this function. Ugh. Oh God, that's nasty. Okay, on the interval, -8 to 8. Fine. Well, first thing I'm going to do is differentiate. Derivative arc sine. Anybody? 1 over square root of 1 minus x squared. 1 minus something squared. That something is x over 8. X over 8, I need a chain rule. 1/8. Okay. Minus a quarter times the square root. That's a 1/2 times this thing to the -1/2. The thing is 64 minus x squared, chain rule minus 2x. The 1/2 is the square root. The square root is this thing to the 1/2 power. I brought the 1/2 down and I'm raising to the -1/2. So far, so good. Okay. Ugh. Oh, that's all right, fine. It's not as bad as it looks. There's this square root of 1 minus x over x squared over 8. And there's a 1/8. That 1/8 is a square root of a 64th. So I can bring that 64 inside of here. And I'm just going to simplify one thing at a time. This is actually 64 minus x squared. This thing. This thing is this thing. You see that? This is a 64 minus x squared, because that 8, if I pull inside the radical sign, I get a 64. And then it's 64 over 8 squared. So that's just x squared. Question? No. Stretching. Okay. I got a minus sign and a minus sign. I got a 1/2 and a 1/2. And then I have a 1/4. And look at this. Okay, good. So that means I can pull out 1 over square root of 64 plus x squared. That leaves 1. And here I'm left with x over 4. That's not bad at all. Okay. Not so bad, not so bad. So my critical values are at x equals -4. And if this denominator is 0, which happens at x equals 8 and -8. Okay, so 8 and -8 are critical values. 8 and -8 I was going to evaluate at anyway, because if we're looking for absolute maxes and mins, I have no idea what this curve actually looks like. Let's just pretend it's something. I have a critical value at -4. So I have like a local max or local min or something, but then I don't know what happens outside of that. I have one point where the derivative is 0, and I have a couple of points where the derivative is blowing up, but the function isn't blowing up there. So I don't know what, this is just a complete guess as to what the function actually looks like. Let's see what we can determine. So the 3 places we have to evaluate the function are -4, 8, and -8, and then we'll know where the absolute maxes and mins are. Right? Does that make sense? Okay, so what is f of 8? All right, I got inverse sine of 1 by the looks of it, minus a quarter times 0, times square root of 0. Inverse sine of 1, I know that. What has sine 1? Sine is equal to 1 at pi over 2. So this is pi over 2. Okay, not so bad. F of -8 is inverse sine of -8 is -1. Again, at -8, I get a 0 here, -0. So -1, let's see, sine we take the sine function. To make the inverse sine function, we take the sine function from pi over 2 to negative pi over 2. Pi over 2 to negative pi over 2. This is sine. So where are we? -1 at negative pi over 2. So far, so good. Now all we need is f of -4. F of -4. Sine inverse of -4 over 8. -4 over 8 is -1/2. -1/2, okay. Minus 1/4 times the square root of 64 minus 4 squared is 16. Ugh. Okay. Sine inverse of -1/2. So where is sine equal to -1/2? I have to draw a picture. This is 1, this is 2, this is √3. That's 30 degrees. 30 degrees is pi over 6. So this is pi over 6 minus 1/4 times 64 minus 16. 64 minus 16 is 48, which I can pull a 4 out of and get left with 12. I can pull a 16 out of all of this. I can pull a 16 out of this. 16 under the radical is a 4, and I'm left with 3. Okay, so I have pi over 6 minus √3. God, pi over 6 minus √3. Very, very, very crudely, pi over 6, pi is like 3, over 6 is like 1/2, and minus √3 is like -1, -1.5. Let's see if I can get away with being that crude. If minus √3 I estimate as 1, am I too crude? Shouldn't that be negative? Thank you very much. I'm down here at negative pi over 6. Thank you, thank you, thank you. Okay, so now I'm at -1/2 and -1. That's at -3/2. That's at -3/2. This is also at -3/2. So who wins? Yikes. This is about 3/2. Okay, so this is definitely the absolute max. These two are negative. This is the absolute max. So absolute max is equal to pi over 2, and it happens at x equals 8. Which of these is the min? Negative pi over 2 or negative pi over 6 minus √3? How are we going to figure this out? Well, one thing we could do is the difference between these two is pi over 3, which is very close to 1, whereas √3 is quite a bit bigger than 1. √3 is like 1.4. 1.4, whereas this is like 3.1. 3.14. So this is really much smaller than, so this is the more negative one. This is the larger negative one. So what we just figured out is negative pi over 6 minus √3 is less than negative pi over 2. Because pi is like 3.1, this is 1/2, and this is 1.4. Just very, very roughly. Again, this one's kind of tricky. So I'm going to say this is the minimum. Am I right? Abs min is equal to negative pi over 6 minus √3, and it happens at x equals -4. Does that make sense? Make sense how you come up with that? Jenny, please. How did I get -4? Okay, so I looked at the derivative. I computed the derivative. And I want to know what the critical values are, which is when the derivative is equal to 0. So I looked at this and said, when is this equal to 0? It's when x is equal to -4, because then this is equal to -1. So if I take -1 and I add 1 to it, that's 0. So when is this thing equal to negative? I mean, I just solved 1 plus x over 4 equals 0. I just want to know, when is this equal to 0 or undefined? It's undefined at plus or minus 8, and it's 0 at -4. Yeah, 5. What did I do with the 1/8? Oh. Uh-oh. Oh, the 1/8. The 1/8, I multiplied, I turned the 1/8. Okay, I did this a little quickly. 1/8 times the square root of 1 minus x over 8 squared. I wrote as 1 over, I pulled the 8 inside the square root. If you pull it inside the square root, that's a 64 minus 8 squared. 8 squared is still 64, x over 8 squared. I just did a little bit of algebra. And the 1/8 turns into 1 over 64 minus x squared. I saw these two things and I said, there's no way to do all this. Something has to happen. This problem is cooked up, right? Someone gave you this problem, which means it's solvable. And it's solvable in the hour that you have to do your exam. So something has to come out nice. I can't have this like 1 minus x squared and a 1 over 64 minus x squared. Those two things will not make for nice algebra. So what's going on? Oh yeah, I have this 1/8 in front, and that 1/8 will turn those two into the same thing. So in real life, life is not so nice. Exam problems are nice. Okay, next. How are we doing on time? We got what, 20 problems to solve and 40 minutes to do it. F is a differentiable function. Suppose furthermore that f of, okay, I got to draw a picture. F of 2 is 4. 1, 2, 3, 4. Right there. And f prime is greater. What does this smell like before I even read anything? What is it? Say it again. MVT. MVT. It smells like MVT. Okay, I have one value. Yeah, and exactly. Okay, use this information in parts A and B. What can we say about the value of f of 7? F of 7. 1, 2, 3, 4, 5, 6, 7. Well, if f of 7 is too low, then this average speed or average rate of change will be lower than -4. And that will make it so low that there will have to someplace be an instantaneous rate of change, which is that value, that same whatever this slope is. Okay, so the average rate of change, from x equals 2 to x equals 7 cannot be less than or equal to -4. If it were, there would have to be a point. If it were, there would be some point C in 2 to 7 with f prime of C equal to or less than or equal to -4. Less than or equal to -4 by the mean value theorem. You don't have to write all of this out. Just say, yes, I'm using the mean value theorem. I'm just trying to give a better value of this. Okay, so f of 7 minus f of 2 divided by 7 minus 2 must be less than or equal to -4. Sorry, cannot be. So it must be greater than, right? An instant. This is equal to f prime of some point, but f prime is always at least -4. So what does that mean? If I multiply both sides, so this is 5, so I'll multiply by 5. F of 7 minus f of 2 is at least -20. F of 2, I know, f of 2 is 4. That means that f of 7 is at least -16. Yeah, does that make sense? So what can we say about the value of f of 7? It can't be less than -16. If it drops to less than -16, then that's the straight line. Okay, what about 1? What about the value of 1? So this was part A. Part B, what about the value of 1? Again, if I apply the mean value theorem, it says that f of 2 minus f of 1 divided by 2 minus 1, that's going to be the derivative of some value. That derivative must also be greater than -4 by the same principle. So if I multiply through by 1, this is just 1. I don't have to multiply anything. F of 2 is 4. F of 2 is 4. So I'll add -4. I'll add 4 to both sides. Let's add 4 to both sides. And let's add f of 1 to both sides. F of 1 to both sides. This says that f of 1 is less than 8. F of 1 must be less than 8 by that same exact principle. What does that mean? If f of 1 gets larger than 8, If it gets larger than 8, then the average slope from 1 to 2 is so low that there has to be some point in between with an instantaneous slope less than -4. Okay, so we constrain f of 1. F of 1 is constrained from above. It can't be larger than 8. F of 7 is constrained from below. It can't be smaller than whatever it was, 16, -16. Does that make sense? How many of you would have gotten this one on the test? Okay, good. So if the answer, if you didn't hold up your hand, you have a couple days to practice. Suppose f is an odd function differentiable for all real numbers. Okay, fill in the blanks. Ooh, good. If f of 1, I like this. If f of 1 is -29, -29, okay, so here's my point, 1 comma -29. The mean value theorem says that there's some tangent lines. I need 2 points to do something with the mean value theorem. I only have 1 point. It's odd. It's odd. That means it's at -1. It takes the value -29. Odd means a rotation, 180-degree rotation about the origin. So I have a +29 up here, and here's the point -1, 29. So what's the average slope? Average slope is what's my rise? My rise is 29 times 2, whatever that is. I guess -29 times 2, right? I dropped by a factor of 29 over what length? 2. So the average slope is -29. So the mean value theorem says there's at least one tangent line to this graph. All I know about it is differentiable. I have no idea what it's doing anywhere else. Well, that's not even a function, but you know what I mean. Whatever it's doing, there's some points. There's at least one tangent line to this graph with slope equal to -29. The instantaneous slope is achieved at somewhere. The average slope is achieved instantaneously at some value. We don't know.
No, sorry. When was the mean value consider anything else?
It wouldn't.
It was.
Yes, it wouldn't. Okay, does that make sense? There's at least one place where I mean, if you had like more points, then here we only have 2 points. If you have a whole bunch of points, then between each one of them is a mean value theorem. Here we only have 2 points, so I don't know why. It's a test. It's a test of your understanding of the mean value theorem. Next. Okay. Number 7. Ugh. Find f prime. Fine. That by now we're very good at finding f prime. So let's do it. There's an x squared. So I'll differentiate that first. 2x e to the -7x plus I'll leave the x squared alone, and I'm differentiating e to the something. That's e to the something. E to the it's to whatever. And then the chain rule, -7x derivative of that is -7. I can combine those. There's an e to this -7x in both of those. There's an x in both of those. What's left over in the first bit is a 2. What's left over in the second bit is -7x. That's just for future reference. There's no need to simplify. This is part A. Part A is already here. Let's continue the calculation because I'm sure it's going to ask me for the critical values. What are the critical values? So when is this not defined? Never. When is it equal to 0? So B, critical values. Yes, exactly. Critical points, critical values. I don't like the use of points for values, but it is what it is. Critical values are at x equals 0 or 2/7. Sid, is that a question? A little louder. Yeah, it seems to me that even when the book asks for critical points, it still only is asking for the x values. That's why I don't like the use of the word points here. You can, if you put the ordered pair, you certainly will not lose any points because you knew the x values. But I would call these critical values, not critical points. But I seem to be in the minority. I think people use the vocabulary critical point to mean the x value. I would call that a value, not a point. Okay, whatever. Find the open intervals where f is increasing. Great. Well, let's look at the sign of f. I'm sorry, let's look at the sign of f prime to know whether f is increasing or decreasing. So what's the sign of f prime? What's the sign of this thing? E to any power, positive. Okay, so we don't even have to look at that. Our values are 0 and 2/7. We've done this many times, but okay, let's do it again. If we have a huge positive x value, this is positive, this is negative. So it's negative when we get up high. If we have a huge negative value for x, this is negative, huge negative value times -7. This is positive times a negative, that's a negative. My guess is, so if I put in, no, I don't want to put in a value. If I'm bigger than 0, then that's positive, but I'm less than 2/7, so this remains negative. I'm less than 2/7, then I'm subtracting off less than 2 from 2. So this is positive. So I have a positive and a positive. Okay, so find the open intervals. It's good that they said open. We don't have to think about the endpoints. So C, the open intervals where f is increasing. Where is f increasing? 0 to 2/7, where the first derivative is positive. 0 to 2/7. Open. Beautiful. D, find the open intervals where it's decreasing. Yeah, -infinity to 0, union 2/7 to infinity. Question.
What are stations Maddie said that you're not supposed to do to see the column because it's not actually.
Find the open intervals where it's decreasing. This is, well, oh. Yeah, she's right. She's right. And I'll tell you why. If it said find the domain where f is decreasing, this is the total domain on which it's decreasing. It says find the open intervals. What are it's a list of intervals on which it's increasing. So you put commas. She's right. She's right. Again, language is important. Yeah. Find the local minima and their locations. Find the local maxima and their locations. Okay. I would read local minima and local maxima here as saying, what is the local minimum value? Not just the location of the local minima, which says the x value, but the local minima. Here I would read, actually, it seems to me, again, the English language is so fraught with imprecisions in ways that mathematics is not allowed to be. So which is it? All right, fine, whatever. We're decreasing and then we're increasing. This is a local min. We're increasing, then we're decreasing. This is a local max. So local, so E was about min. E is local min. We have a local min at x equals 0. F of 0 shouldn't be that hard to work out. F of 0 is 0. So 0 is a local min. And F is a local max at x equals 2/7. This might be a little more painful, but actually, no, you just put in 2/7 for the function. I get an e to the -2 and a 4/49, although there's no reason to simplify. F of 2/7 is 2/7 squared e to the -2. Certainly, if you put both of those, you can't be wrong. Okay. There's no, you don't worry about simplifying. It is what it is. Those are the local maxes and mins. We're done. And their locations. Any questions? Next. Here's a graph. This is a graph of the derivative. Okay, it's a graph of the derivative. Can you guys see that at all? Should I zoom in? No, you can't see anything. Let me just pencil it in a little darker. Okay, that's the derivative. This is y equals f prime. It's a graph of y equals f prime, the derivative. It's the graph of y equals x prime. A question about a continuous function. Again, use the graph. Okay, what are the intervals where f is increasing? Again, intervals. So it's not a union of, it's not the region, but it's a list of intervals. So let's separate them by a comma. Find the intervals where f is increasing. It's increasing when the derivative is positive. Now, I've drawn it slightly sloppier. It looks like it actually hits 0 at 0. This is the point -4. That's the point 7. This is the point 7. This is the point -4. Okay. So it's increasing on -4 to 0. And another interval where it's increasing is 0 to 7. 0 to 7, instantaneously at 0, it is not increasing. Peter. I would argue with that. At that instantaneous point, unless maybe it's how I've drawn the picture. No, it's 0 at 0. You're not increasing if you're 0. I would argue that one. Okay, I would argue that one. Oop, undo. Here we go. Okay, so that's part A. I would not say that it's increasing at 0. It's temporarily, I mean, it's still, it's not, it's very, what happens at 0 is this. It instantaneously pauses for a second. I guess it could be thought of as increasing because it, everything to the right is smaller, everything to the left is larger. Yeah, they're right. Yeah, -4. You see why? You see why? So -4 to 7. Okay, so here's a rule that you can think of. If it's positive to the left and to the right and just instantaneously is 0, then it's something like this. So that really is increasing. Every point to the left is larger, every point to the right is smaller. I said that backwards. Every point to the left is smaller. What I pointed to is right. Now, don't think about the things coming out of my mouth. On which intervals is it decreasing? So I guess we're assuming, we're not assuming the function just dies at -9. It keeps going forever, presumably, right? Presumably we just have a continuation. So here, I guess I would say -infinity to -4. I would not say that it's increasing. I mean, not say that it's still decreasing at -4, comma, 7 to infinity. Yeah. Okay. Where is it concave up? A function is concave up when its second derivative is positive. Second derivative positive is concave up. So second derivative is positive is when the first derivative is increasing. So where's the first derivative increasing? So, okay, so this is f prime is increasing. Now we just look at the picture. Where is f prime increasing? Up to -2, right? -infinity up to -2. And where else is it increasing? From 0 to 4. So from 0 to 4, it's increasing, and that's it. Okay, so that's concave up. Concave down is f prime is decreasing. So that's the rest of it. It's decreasing from -2 to 0, -2 to 0, and it's also decreasing from 4 out to infinity. That's where it's decreasing. Okay, what are the critical points of f? Critical points of f are where the derivative is 0. So that's -4, 0, and 7. So the critical points are -4, 0, and 7. I would, again, call them critical values, not critical points. Find the locations of any local maxima. Locations means x values. X values of local maxima. So that's a local max is when I go from being, local max is when I go from increasing derivative to decrease. I mean, positive derivative to negative is a local max. So where do we go from being positive to being negative? 7. 7, we go from being positive to negative. So that's x equals 7 is a local max. Local max. How about local min? Local min is if I'm decreasing and then I start increasing. So if I'm decreasing and then I start increasing, that's at -4. At x equals -4. Okay, any questions on this one? Make sense? Next. Number 9, suppose a function has that derivative. Okay. Well, we know about antiderivatives, so let's, before we even read any further, antiderivatives, it's hard to take an antiderivative of a product like this. Let's multiply things out. Raga. Yes. Yes. We are including 0. We are including 0 because think about what increasing means. Increasing means if I take a step to the right, I go up. If I take a step to the left, I go down. So at that point, if I take a step to the left from that point, the value goes up. If I take a step to the right from that point, the value goes down. So because the first derivative is positive on both sides, we're going to call that increasing. Okay, there's an argument to be made. What happens instantaneously? Instantaneously, you're not, thank you, you're not speeding up or slowing down, but that one instant. But everywhere to the right is lower than you, everywhere to the left is larger than you. That's increasing. Yes, x cubed is an increasing function. At x equals 0, its derivative is 0. But everywhere to the left, let me draw the picture. So it's a question of vocabulary. What are we going to call increasing? We're going to say a function is increasing. So let's recall the definition of increasing. Definition. F, let's say f is increasing on an interval a to b if whenever you have some point x1 and x2 between a and b, f of x1 is less than or equal to f of x2. And maybe we'll say strictly increasing if this is a strict inequality. Okay, so think about the graph of x cubed. So here's y equals x cubed. At this point, or on this interval, -1 to 1, or minus infinity to infinity, is it true that anytime I have one value x1 and another value x2, including at 0, that the value of the rightmost number is higher, the value of the function at the rightmost higher is higher than the value of the leftmost? It is true. So that's why the function does satisfy the definition of increasing. Okay, so this is some stupid edge case, but we have to be aware of these things. So here I put less than because I want two different values, x1 and x2. And here, well, yeah, some people would say this is non-decreasing or strictly increasing as opposed to strictly increasing. So even if I put a strictly less than sign here, that's still true in the case of the function x cubed and in the case of our function up there. I am strictly increasing. Anytime the value of x1 changes, the value of the function changes and changes in an increasing way. Okay, so this would be strictly increasing if you want to be pedantic about it. Okay, good. Next question. Hard. Yes, so it is still strictly increasing. Even though the derivative at 0 is 0, it's increasing to the left and it's increasing to the right. So it is strictly increasing. If you take any tiny amount, even as you cross this point 0, any tiny step from some x1 to some x2, the function will increase. Even though instantaneously it's not increasing. The function itself is increasing because the derivative is positive on both sides. Okay, good. It's good to clarify these things. But they're edge cases. They're not the main subject of calculus. It's more about language. Okay. All right. Good. Number 9. Let's go. I'm going to multiply this out. 16x squared minus x cubed. I know how to anti-differentiate that. This must have come from an x cubed over 3 times 16, because the derivative of x cubed over 3 would have given me 16x squared. This must have come from an x to the 4th over 4. And, well, any other antiderivative would differ from this one by a constant. Okay, so before I do anything, I'm told what f prime is. Hey, in this case, I can actually look at the function. Okay, find the domain of f. Domain, there's no problem with any of these functions, polynomials. So the domain is all real numbers, R, or if you like, minus infinity to infinity. Find the critical points. Great, you told me what the critical points are. They're 16 and 0. X equals 16 and 0. Those are the critical values. Find even those again. Yeah, let's move on, right? You can figure this out. Okay, so there was no reason to I did this just for practice, I guess. But again, you just look at whether it's positive or negative. We've done this enough times. If we look at the derivative of this, that'll tell us about concavity. But are you going to have antiderivatives are chapter 4.8, and we covered chapter 4.8. Yes, antiderivatives are fair game on the midterm. right? We talked about him. We had a homework about him. Okay, compute this limit. If you do use L'Hopital's rule, be sure to indicate how it's being applied and whether it really is an indeterminate form that allows its use. Okay, and please keep your limits perfectly annotated so that we can see what's going on. Okay, I have a limit. I'm just going to rewrite it here so I have room to work. Sine of 8x minus 8x over 14x cubed. What's happening to the numerator? That's going to 0, that's going to 0, that's going to 0. So this is going to 0. What's happening to the denominator is 0. Okay, so indeterminate 0 over 0 form. So I can use L'Hopital. Now, whether I succeed in using L'Hopital remains to be seen. So I don't know if I'm justified in saying this is equal, but I'm going to differentiate the top and bottom. The derivative of this is cosine of 8x times 8 minus 8 divided by, I'm not going to multiply that out, 14 times 3, whatever that is, x squared. Now, what's happening here? Cosine goes to 1 as x goes to 0. So I have 8 minus 8. This is still going to 0. What's happening to this? This is also going to 0. So I still have an indeterminate form, indeterminate 0 over 0 form. I'm going to L'Hopital it again, exactly. So this equality is not justified yet. It might be after a few more operations. Limit as x goes to 0. Now I'm going to differentiate this. The minus 8 is gone. Cosine is a negative sine of 8x. Chain rule 8, constant 8. There was that constant 8 that just stayed there, and there's a chain rule 8 that came out. And what about the denominator? 14 times 3 times 2 times x. This goes to 0. This goes to 0. It's indeterminate 0 over 0. So I still don't know if I'm justified in doing any of this, but let's take, I think, one more. I see that one more will give me a number on the bottom. So I definitely am running out of L'Hopital's. What's derivative of negative sine? So I have negative 8 squared. Let's just keep that as constants. And the derivative of sine is cosine, 8x, chain rule 8, over, this is 14 times 3 times 2. That's it. It's no longer indeterminate. Cosine goes to 1. And so the limit here is negative 8 cubed over 14 times 3 times 2. I'm not doing that algebra. That is a number. It's not algebra, it's arithmetic. I'm not doing that arithmetic. That's some number, which means this was justified, which means that was justified, which means that was justified. And that is the final limit. Did I drop a minus sign? So from here to here, there's a cosine, and then an 8 comes out. From here to here, that minus 8 just differentiates to 0. And this differentiates to minus sign. And I collected the minus 8 times 8 here and differentiated the sign, getting a cosine 8x times 8. Where am I missing something? I'm good? Looks okay. Did they leave it like this, or did they simplify this? I mean, you can take a couple of 2's, you can cancel some 2's on top of, there's no reason for this. I'm not checking your algebra skills, arithmetic skills. This is algebra. Okay, that was number 1. Should we do all of them? You need practice on all of them? Which one? C? B? Let's do B. Okay. I'll write it here and then I'll move it down. Natural log of x minus 5 and limit as x goes to 6 from above. Now I can grab it and move it down. Okay, good, that worked. So B is this limit. All right. This is going to 0. This is log of 1. Log of 1 is 0. So I'm going to have to put this into L'Hopital's form somehow. I need a fraction, common denominator, exactly. Limit as x goes to 6 from above. Why from above? Because this has a different behavior at above or below. This is going to plus infinity from above, but minus infinity from below. Okay, so let's make sure we remember that it's from above. Common denominator, I have natural log of x minus 5 minus x minus 6 over x minus 6 times natural log of x minus 5. Right? I just cross multiplied, and that's my common denominator. The numerator is still going to 0. The denominator is also going to 0. I have an indeterminate form. So, indeterminate 0 over 0 form. I try to apply L'Hopital. Bernoulli, L'Hopital, whatever, too late. Limit as x goes to 6. Oh God, the derivative of this is going to be 1 over x minus 5, no chain rule, minus 1. Oh, it's not so bad. What about the derivative of that? Okay, which one should we do first? Let's differentiate this. That's easy. That's a 1 times natural log of x minus 5 plus, I'm going to leave this alone, x minus 6, and I'm going to differentiate that, which is x minus 5. Not bad, not bad. This, oh yeah, this goes to 1, that's minus 1, that goes to 0. Numerator is going to 0. Do we have to do L'Hopital again? This is going to 0, and that's going to 0. Damn. Okay, so still indeterminate. Bernoulli's rule. If we're saying damn, we can call it L'Hopital. I need some more room. Add a page. Okay, let's keep going. We're still indeterminate. Still indeterminate. Okay, so can we do Bernoulli? Can we do the nice guy Bernoulli? Now wait a second. Before I try to evaluate this, because I'm gonna get some nasty stuff if I try to evaluate this before I simplify. Before I evaluate this, let me multiply top and bottom. So this is not a question mark. I'm not doing L'Hopital's rule. I'm just going to multiply top and bottom by x minus 5. Right? That's just algebra. So let me multiply through by x minus 5. Otherwise, I think I'm going to get some nasty stuff. So let me multiply through by x minus 5. So multiply top and bottom by x minus 5. That will give me a 1 minus x minus 5 on top. On the bottom, it'll give me x minus 5 times log of x minus 5 plus x minus 6. You see why I did that? Not only will that make my life easier, I think we actually have to do that because when we start differentiating, we'll get more and more crap up here. We're never going to see. Now I have a polynomial on top. I know one more derivative and I'm getting a constant that's not 0. As opposed to continually getting more and more nonsense in the numerator. You see? All right, now it's still indeterminate. We didn't do anything. As x goes to 6, this still goes to 0. This still, yep, goes to 0. So we can apply L'Hopital. Now we're applying L'Hopital. I'm going to keep saying L'Hopital. The hospital. Derivative of this is -1. Derivative of this, I got a 1 here. That's easy. Let's do a +1 at the end. And then, okay, it is what it is. So I have x minus 5. Actually, this is kind of funny. X minus 5 over x minus 5 plus, if I differentiate x minus 5, I get 1 times natural log of x minus 5. Everybody see what I'm doing? I think now we're golden. This thing's going to 0. As it has been all along. Now I get a 2 on the bottom and a -1 on top, so I get a -0.5. The -1 is just, this is a constant. This is a constant. I differentiate 9 minus x, I get -1. So this was a really important step. The multiplying the top and bottom by x minus 5 and not just blindly continuing to differentiate the top and bottom was a really important step. It wasn't just a simplifying thing. If we had continued differentiating, we would get more and more powers of x minus 5 here and here. I think I haven't tried it, but there are instances like this where if you don't simplify before you apply L'Hopital as much as possible, you go around in circles. You never actually get to a value. Finally, a limiting value, which justifies that use of L'Hopital and justifies that use of L'Hopital, and now we're back to the beginning. There's the answer. Was there a hand, Peter? No, I thought I saw a hand somewhere over here. No. Okay, you want to do one more of these? No, you've had good practice with them. You would know how to do. You know how to do this? No. Well, I asked you if you want to do one more and you said, no, we're good. No, you can't skip that one. Come on. It's not bad. Look, if the function is differentiable, right? What happens? It's at 0, it's becoming 0. So this is giving me tan of 0 is 0. So I get f of 0. That's going to 0 on top. How about on the bottom? Again, get f of 0 times 9x, that's 0. So 0 over 0. Let me write it out. Let's do number D. This, how would you do this? Yeah, you take logs, you'd work out what the limit is, and after that, you would raise whatever limit you got to the e. You would raise e to the power of whatever you got in the limit. Fine. F of tan of 6x divided by 9x plus f of sine x, limit as x goes to 0, with f of 0 equals 0 and f prime of 0 equals 13. Okay, let's grab that and go for a ride. Okay, number C. Number C, letter C. Okay, so these are our two pieces of information. The numerator is going to 0, the denominator is going to 0. It's indeterminate. We're going to apply L'Hopital. So let's try differentiating the top and bottom. If I differentiate the top, f prime at tan of 6x, the derivative of tan is secant squared. Secant squared of 6x, chain rule, times 6, good. Denominator, derivative of 9x is 9. Derivative of f is f prime of sine of x. Derivative of sine is cosine. Okay, I know that f prime of 0 is 13. So this is getting closer and closer to 13. I mean, I wrote it like this, but I mean, the limit is what we were given. What's secant of 0? Yeah, 1 over cosine of 0. This is going to 1. So far I have 13 times 6. So in the numerator, I'm getting 13 times 6. In the denominator, I have a 9 plus cosine is going to 1 and f prime is going to 13. Beautiful. Done. That's the limit. We're justified. End of story. This was D. You wouldn't skip this one. Come on. No, do not simplify 13 times. Don't waste your time doing 13 times 6. I mean, it's subtle. There's an art to what you want and don't want to simplify. An answer like this, once that's it, just leave it. This can't possibly, I'd love to say this can't possibly lose points. Jenny. Can we do the cylinder inside the circle? Yeah, let's make sure we make time for that. Okay. Can I skip this? This is the same kind of thing. It's L'Hopital, except you have to read the values of the function and its derivative off of the graph. It's exactly what we just did. Right? Let's skip it. Yes? Okay. There's a barn. You want to get right to the cylinder. Jenny is voting for the cylinder. So let's come back. If we have time, we'll come back to the barns. Okay, this is the one, right? I have a right circular cylinder. I have to draw a right circular cylinder. Right just means, you know, what's not a right cylinder? Well, this I wouldn't even call a cylinder, but for some reason, we're specifying that it has a right angle here. Okay, there's our cylinder. We have a right circular cylinder with maximum value that can be described in a sphere, can be inscribed in a sphere of radius 10 centimeters. Oh boy. All right, what's the volume of a sphere, a volume of a cylinder? Pi r squared. H, good. If this is the height, so the volume is pi r squared h. The fact that it's inscribed in a sphere means that, what is this length? H over 2. What is this length? 10. And what is this length? Right, and it's also r. So r squared plus h over 2 squared is equal to 100. That's how we're capturing. Does this make sense, Jenny? This is how we're going to capture the fact that it's inscribed. So the fact that the cylinder is inscribed in a sphere implies this relationship between the radius and the height. Yes? Okay. That means I can solve for r squared. So r squared is equal to 100 minus h squared over 4. You see why I want to solve for r squared and not h? Because I have an r squared. So we're eliminating one of the variables. The volume is pi h times r squared, and r squared is 100 minus h squared over 4. Okay, so this is the volume as a function of h. So let's think about this. If h is equal to 400 square root of 400 is 20. If h is equal to 20, if the height is 20, well, 20 is from here to here, right? From the top to the sphere or the bottom of the sphere. So that's a tiny little, that's a piece of lead cylinder. That's not going to hold any volume. The other extreme is if h is equal to 0. If h is equal to 0, then I just have a disk. That's not going to hold any volume. Those are the extremes. I can read them off right here. So this is going to be a cubic. It's some cubic with a 0 at 0 and a 0 at 20. And then, well, it's positive in between, whatever it's doing. It's some kind of cubic equation. Cubic equations don't do that. Right? It's some cubic. It does something like this. Actually, it has a double root at 20. Oops. It has a double root at 20. So there's our cubic. This is v as a function of h. Does that make sense? So we can just read that off. Okay, and obviously we're looking for this point. How are we going to find this point? Derivative. Okay, so let's multiply this out. I guess I get 100 pi h minus pi over 4 h cubed. And so v prime, or dv dh, let's just say v prime, differentiating with respect to h, is 100 pi minus 3 pi over 4 h squared. Where is this equal to 0? When h is equal to, let's say h squared. H squared is 400 over 3. 400 over 3. So h is the square root of 400 over 3. Okay, that's what it is. That's this value. Square root of 400 is 20. So this is 1 over root 3 times 20. So you don't go all the way to 20. You don't go all the way to 0. You go to 1 over root 3. That's the fraction of 20. Okay, so that's the height. That's the optimal height. What does it ask for? What is the maximum volume? So actually, I don't have to work out what the radius is. I just want the maximum volume. So I want to know what the volume is at this maximum point. So v of 20 over root 3, I go right back to here. Pi times 100 minus h squared is 400 over 3. 400 over 3, h squared over 4. So there's a 4 there. This was h squared. This much was h squared. Then over 4, all times h, 20 over root 3. Leave it like that, or if you like, what is this? 2/3 of 100, whatever. This is the maximum volume. Good, Jenny. A cylinder? Yes. Here. Yeah, let me zoom in on this picture a little bit. Let me try to clarify that picture. Here's my cylinder. Okay. Here's the cylinder. This distance is r. This distance, let's do it from the center of the cylinder, which is also the center of the sphere. The sphere is all around here. So this distance, so we're isolating a triangle inside the cylinder. Okay, this is more of the sphere, the circumscribing sphere. So this distance is h over 2 because it's half the height. And this distance is 10. And this distance is r. And that's a right angle. Does that make sense? Because the whole height is this. This is the height. So this is just halfway, and here's another halfway. Yeah, through the center. Yeah, Dan.
I got plus or minus 20/√3. Do we have to even test negative?
Very good. Very, very good. So the fact that we had an h squared here means in principle that h could be plus or minus this value. I threw away the minus value, minus 20/√3, bless you, Yusuf. I threw this away because it's not physically possible to have a negative height, and we're only interested in heights between 0 and 20. Yes, so we throw away, there's a plus or minus, and we throw away the negative value. Very good. Jenny, did I answer your question? Yeah, it makes sense now where this triangle came from. Okay, 5 minutes left. Which one do you want to do? You want to do this one? A small island, Jesus. Okay, 6 miles from the nearest point P of a straight shoreline of a large lake. Okay, so here's a lake. This is water. Here's my island. And this distance is 6 miles to the nearest point of the shoreline. If a woman on the island, okay, so we have a woman here, she can row a boat at 3 miles an hour. So she's got a boat, and the boat can travel at 3 miles an hour, and she can walk 4 miles an hour. Where should the boat land in order to arrive at a town 11 miles downshore? So 11 miles downshore from the point P. So here's a town, let's call it T. Here's our town. It's right on the water, I'm assuming. It's 11 miles downshore from the point P. This is 6 miles, that's 11 miles. Okay, she has 2 options. Row the whole way. She has 3 options. She can roll the whole way, right? She rows at 3 miles an hour. Or she can row straight to P and then walk. She walks at 4 miles an hour. Or she can do something in between to try to optimize. You know, this is the largest distance that she would cover. This is the shortest distance, but she rows slower than she walks. So where's the sweet spot between how far she should walk and how far she should row? That's what we need to determine. Well, we have to give ourselves a parameter. What should we call this height? X. Yeah, let's call this the landing point. How far downshore from P she lands? X. Okay, X is where she lands. Where she lands. Okay, she wants to minimize the time. I assume she can row this in order to arrive at the least time. Okay, so what is time? I use T for the town. The town is now a city, and we're doing time. Okay, so how much time? What's this distance that she travels? D1, let's call this D1. Distance 1 is, this distance is X. This is 6 miles. Square root of X squared plus 6 squared. That's a right angle. That's distance 1. Distance 2 is 11 minus X. 11 minus X. Right? This is distance 2. How fast does she travel, or how much time does it take? If this is the distance and her speed is 3 miles an hour, how much time does it take? 3 miles per hour. So I want to divide miles per hour. So it's distance over speed is time. Right? Distance over speed is the amount of time it takes to cover the first leg plus distance over speed. Does that make sense? And again, you can use dimensional analysis to help you out here. This is distance, this is miles. This is speed, miles per hour. So the miles are going to cancel on top and bottom, and the hours will come to the numerator. All right, and now you can differentiate this, set it equal to 0. You'll figure out where she should land, and then you'll know how much time it'll take. Where should she land? Okay, so X is the answer. We're out of time. Anyone who wants to go is welcome to go. If you want me to do one more problem, I can stay and do one more. Do this one? Okay, let's solve the initial value problem of this. If this is the derivative, so I'm told that V prime is equal to 4 is just a constant, 1 over 1 plus t squared plus secant squared, then V I have to anti-differentiate. So 4 is just a constant. Whose derivative is 1 over t squared? Arctan. Thank you. And whose derivative is secant squared? Tan. Plus c in general. Okay, so this is a function of t. But we also know that at 0, it's equal to 2. So v of 0 is 4 tan arctan of 0 plus tan of 0 plus c. Tan of 0 is 0. This is 0. And this is equal to 2. So c is equal to 2. Which means that v of t is 4 arctan plus tan plus 2. All right.